I would like to welcome you, everyone. Thank you so much for joining this seventh edition of RAS webinar series. So we have a pleasure to have Andrea Dariano, who is associate professor at Roma Tre University in Italy. He'll be talking about possibilities and potential of using advanced mathematical modeling, and in particular alternative graphs for solving railway optimization problems. So Andrea is a pretty well-known researcher and scientist in this topic and in the railway community, and it's really a pleasure having him here. So the agenda for today will be, we'll start with the presentation. It will be 40 to 45 minutes. For that time, I would like to ask you to have your microphones muted. Any questions you have, feel free to write them in the chat. And we will address the question in a Q&A session after Andrea's presentation. And one more nice addition we have for you is Andrea is available for an informal catch-up after 5 p.m. So you can stay longer with him if you would like to share some more words. So I would like to give floor to Andrea, and please, you can take over.
Thank you very much, Mr. Chairman. Thank you, Nicola, for inviting me to give this presentation. I actually took the opportunity of the fact that we are celebrating more than 20 years that the alternative graph methodology was firstly introduced in a technical report at Roma Tre University. Since there, it was used in many applications, starting with the production scheduling and logistics applications. Then we developed applications for railway field. And I would like to tell you what we did and what has been done in the literature using this methodology. So this is me. Just spend very few words about the speaker. I am collaborating with several industrial partners in applying this methodology and other methodologies to solve railway optimization problems. I am collaborating with several European railways, including the Dutch railways, UK, Switzerland, Italy. And I'm also collaborating with the European Commission about how to invest the European money on the new infrastructure and signaling system. So the goal of the presentation is multifold. The first item is introducing the alternative graph methodology to a large audience. So I start from scratch, basically, and I want to attract the interest of different type of people with different background. For this reason, I will not go too much further at the end of the presentation because I only have 45 minutes. So I will basically focus on the methodology from a modeling point of view. The algorithmic perspective, I will talk a little bit, but a high level description. So what is an alternative graph? It's a way of formulating job shop scheduling problems. So now the question goes to what is a job shop scheduling problem? A job shop scheduling problem is a very well-known scheduling problem in which you have a number of jobs. Each job corresponds to a vehicle, for example, a train in our case, or a person taking some actions. The job is composed by a set of operations. You can see here with the color the operations on diagonal lines of each job. And then you have that to decide the set of operations that compose the job. This set of operations can be predefined or can be flexible. When we have a flexible composition of job, we have a routing problem. Then each operation is related to a job. and to a resource. And the resources are capacited resources. And each resource is shared by different jobs. If you look at this Gantt chart horizontally, you see that the different colors, the different jobs, are shared by the different resources that are the horizontal information. So horizontally resources, diagonally you have jobs. This is the job shop scheduling problem. Now, the nice thing to say is that it's easy to represent a train scheduling problem as a job shop scheduling problem, where each job corresponds to a specific train, each resource corresponds to a piece of track, each operation corresponds to a piece of track that is occupied by a particular train. And then you have a set of operations that compose the job, that is the train routing or routing. Then how I can use an alternative graph to represent a train scheduling problem. To be simple, we can say that each node of the graph is an operation, corresponds to an operation, and each arc of the graph corresponds to a constraint in the problem. Then why we need an alternative graph? Why we need a special case of graph? Because the train scheduling problem is a problem with special constraints, and one of those is the blocking or no-stall constraint. That means that each piece of track can be only occupied by one train at a time. Okay, if we assume that, then we need to use a special type of graph that is able to incorporate blocking constraints. Here you can see that the gray piece of track, that is a block section between two signals, can only be occupied by one train. For example, this train can run as a green light, and the other one is blocked, cannot go. And this capacited resource can be nicely represented with an alternative graph. Okay. Then, of course, you have other type of constraints. Here I start mentioning these constraints that are related to minimum and maximum time to process an operation. This type of constraints are very general and can include a lot of business rules. And in scheduling theory, minimum time constraint is a release time, when I can start processing an operation, and a maximum time can be interpreted in two ways. A soft way is a due date, that is a time that I wish to complete an operation, but I can also complete later, so delay the operation. Then there is another interpretation of maximum time that is a deadline. Deadline is an hard constraint. I must complete the operation within the maximum time. So I have boundaries, minimum and maximum time that I can model, and this can be used to model several types of business rules. Then I have a lot of other types of constraints. I can mention constraints related to different jobs, like service connection constraint. There can be a connection between two trains in a station, and this can be represented. Or we can represent rolling stock constraints. Two jobs represent two services, and the two services are connected because they use the same rolling stock. And then you have arrival departure time constraints in stations, and you have resource availability constraints. For example, resource can only be used in certain time windows. And then you have minimum maximum travel time constraint for each train in each track or for each operation, and so on. Then what are the modeling assumptions if I was to use this modeling technique? I try to explain them now. First, we need to think that each operation has a start time. So each operation has a connected timing variable, okay? Timing variable is a key type of variable for our problem. And we have a duration time of each operation, and that is an input data. So we assume that we know the duration of the operation. So this type of graph is a deterministic graph. And then we have train sequencing to model. Train sequencing is modeled by a pair of alternative arcs. Alternative means that either one train goes first or the other train. Here you have a situation in which A and B are sharing a resource, and you can use this special type of arcs to model this decision, this sequencing decisions. So either B uses first the resource, and then you have to insert an arc. B is the red chain of nodes, A is the green one. And so if you have that the red goes first, then you will insert this arc in the graph. This means that only when the red goes out, then you can enter with another train, the green one. Vice versa, you have green goes first and the red goes second. Then the third type of variables are the routing variables. Here we can assume that you have fixed routing, so you have no routing variables, or you can have a possibility to locally rerouting trains, or even globally rerouting trains. In this example, you have one route going from left to right, and then you might have some alternative local routes, you see. So you might have the possibility to change the routing of the train. This possibility can also be modeled at a global level. So the difference between local and global rerouting is that the global rerouting changes a lot of resources, while the local rerouting just change resources locally at some stations, for example. So these three types of variable, timing, sequencing, and routing variables are basically the three types of variables that we have to handle with this type of problem. Then you have other type of assumptions that you might incorporate in your modeling that are related to the arrival departure times. This can be at stations, of course, can be fixed, so predefined, or can be flexible. If you introduce a level of flexibility in the arrival departure times, you can have an additional way to optimize traffic flows. Here I can give you a pointer to a paper on transportation research part C, in which I was assessing this type of flexibility. Then we need to incorporate constraints of other type, for example, about the running times of trains on the dwell times at stations, and you can use minimum and maximum values for those times. You can play with these values. If you want, for example, to have a predefined running time for each train, then you can use minimum and maximum values as the same values. In this way, you block the running time of train, and this can be used to simulate so-called green wave, so a chain of green lights for some trains. For example, if you have a heavy freight train that must cross a track, then you might want to run this train at a predefined speed without decreasing, accelerating the speed, because it's very costly. And then you can model this through carefully setting the min-max values for the running times. Then you have other assumptions related to the granularity of time and granularity of resources. This is very important key issue. Of course, if you have a very high level representation of your infrastructure and time, then you can handle a very large network. For example, an entire country in Europe. We did experiments in the Netherlands. Then, or if you go to the very high, very low level of granularity, because, for example, you want to control the speed of trains, then your network will decrease more and more in size, till a network that is just a junction. So the assumptions on the granularity are very key assumptions when you want to model your problem. Then what do we have to do when we have to solve the problem? We have to deal with an important issue that is feasibility of the schedule. The more you add constraints, it's natural saying that the more you expect having problems to find a feasible solution. And indeed, it has been proved that computing a feasible solution is an NP-hard problem with this type of problem that we are studying. Of course, this type of problem is related to the granularity of the network representation, and more in general is related to the number of sequencing and routing variables. Here in this example, just to illustrate you an example of alternative graph where you have problem of feasibility, you have two dotted arcs that are alternative arcs. You must decide one of the two to insert in your solution. And if you insert this arc, you might end up in a cycle. You see here. The cycle is used by this methodology to detect infeasibilities. But if you want to, then you select the other arc, that is this other one, you again have a cycle. So you realize that when you are selecting this pair of dotted arcs, you are going to an infeasibility in any way. What do you have to conclude? That the other constraints, the fixed arcs, the continuous arcs that you inserted in your graph, that do not represent a feasible solution. Now, this type of cases, situations happen very often, especially when you are designing a timetable. You want to add more and more constraints, more and more business rules. At a certain point, you will end up with an infeasibility. And this type of technique, by detecting positive length cycles in the graph, helps you to detect the infeasibility, to detect which constraints might cause an infeasibility. And then you might change those constraints to recover feasibility. So there is a line of research that is dealing with feasibility recovery issues. Then objective function. Usually the objective function is related to the timing of the operations. So this is, for example, related to the completion time of the schedule. So having maximizing throughput, or can be related to the delay of the operations, and all these type of objective functions are related to timing. Why do we use this type of objective function? Because of course these are important, this problem, but also because we can use scheduling theory results on this type of objective functions. So this type of technique, alternative graph technique, is very powerful when you are dealing with timing of operations, minimizing, for example, the make span is an example in the picture. You see that the minimizing the make span might correspond and finding the longest path in your graph. Then, of course, you can optimize other objective functions. This is possible. The type of formulation is very flexible, very general. But if you change type of objective function, you might lose some nice theoretical properties. And it might be more complex to solve the problem to near optimum. Of course, if you use an alternative way to represent this type of problems, not like alternative graph, but like general mathematical formulations, then you can use general solver to solve this problem. You might formulate more general objective function, but general solver often have the problem to converge to near optimum. Now, I move to another item in my presentation that is related to literature. Let's see what has been done in the literature in terms of railway simulation and optimization topics that make use of this methodology. Okay, so what type of model exists in the literature? If you look at the literature on train scheduling, you might find a lot of possible ways to model, of course, this problem, but the researchers are more and more concentrated on two types of formulations. One is a mixed integer linear programming formulation, and another one is the alternative graph representation of the problem. In the mixed integer linear programming formulations, a number of formulations this type are inspired on the alternative graph as well. So we will see during the presentation that it is possible to transform the alternative graph in a MILP. So there is a majority of the approaches that are using this type of methodology. More in deep, there are two streams of research on the mathematical formulations of the train scheduling problem. One is resource dependent, and another one is time dependent formulation. There are also hybridization of these two types of formulation. Now, the problem, of course, is the granularity again. So if you go for a resource-dependent formulation, the resource granularity might impact your solving process. If you go to time-dependent formulation, the time granularity might impact on your solving process. Then, what type of solving methods we can apply to solve this train scheduling problem? You can use a commercial solver that is, in general, as a positive point, can represent any type of business rule and any type of objectives. What is the drawback here is that the solving process might be slow when you increase the problem size. It can be possible that you solve very nicely small scale instances, but when you go to the more interesting real world instances, you can hardly solve them with a general solver. So there were other possibilities to develop a smart or better problem dedicated solver. I will show you one possibility through the alternative graph. And the pro is the scalability. Usually the problem dedicated solver are better scalabilities to solve real world instances, and also very often good performance according to your objective function. The control, the drawback is that when you change the business rules, when you change the objectives, this might have a strong impact on your solver. So the solver might need to be adjusted seriously to deal with different types of rules and objectives. Now, as a problem dedicated solver, we will talk about one that is based on an alternative graph. And usually this type of solver is a mix of different type of algorithms to deal with the three types of variables: timing, sequencing, routing variable. And we will see that we will use either heuristic, meta-heuristic, or exact methods to handle this different type of variables. And I will mention that the algorithms that you use will need to be adapted when you change the constraint and objectives. Sometimes it's easier, sometimes it's more complex to deal with a new business rules and objectives. Now, in both cases, I would like to mention an additional thing that is either if you use commercial solver or smart problem dedicated solver, in both cases, it's good to have a good preprocessing, an intelligent preprocessing. That means a way to understanding which are really the variables I need to optimize in my problem. With your knowledge on the problem, you might be able to filter the variables, so to reduce the number of variables, even to pre-select some values of some variables. And for example, for the routing, there is a literature dealing with filtering the train routes, just finding the subset of routes that are most interesting for optimizing your objective function. Doesn't make sense to use all possible combinations of routing variables. So preprocessing is usually a key of success. If you have a good preprocessing, that is a good customization of your solver, either general or dedicated to the problem that you are solving, then both type of solver might have better performance. Then, of course, when you increase the problem size, when you want to deal with more and more practical problem, you must decompose the problem. I want to briefly mention the types of decomposition that you might use. For any type of decomposition I will mention, you need to solve the problem in an iterative fashion, where you need to deal with the convergence factor. When do I converge to a feasible solution? Or you need to deal with how I can improve the performance through this problem decomposition, or how can I deal with the scalability? How can I decompose the network to be solved for different type of scales? Then, what type of decomposition? I want to mention the temporal decomposition. This is usually very much used in the real-time operations, where you decompose by time your set of variables. And then you solve the problem many times, where every time you choose a different subset of variables depending on the current time horizon of optimization. traffic flow optimization. And this can be implemented, for example, through a rolling horizon approach or a model predictive control approach. Then the other type of approaches is based on the spatial decomposition. And then you define, for example, your network as composed of a number of subnetworks. You can be also inspired from the practice. And then you might develop a coordinator to converge to a globally feasible solution among the different subnetworks. Or you may end up with some theoretical approach. For example, you can use a Bender decomposition where you control the overall network, and then you have sub-problems solving sub-networks. Then you might decompose your problem by type of variables. This is also another way of solving your problem. For example, you can divide the problem in timing, sequencing, routing variables. I can mention here, for example, the European project Combine, where they develop different layers. First layer is trying to recover for real-time traffic control. First layer is trying to recovering the situation when there are delays by re-optimizing speed, timing variables. Then if it's not enough, then apply sequencing. And then if it's still not enough, then apply also rerouting. Okay, so you can decompose by type of variables. Another type of decomposition I want to mention is, to be more general, as a decomposition in sub-problems. The sub-problems might have a combination, for example, of timing sequencing variables, timing sequencing routing variables to solve a specific sub-problem. And then you might find a way to coordinate the resolution of the sub-problems. Then third item of my presentation is about applications. I will firstly give an overview on the applications, most of them based on my personal experience, but also will try to mention some other researchers. And then I will focus on the fourth item on a specific application. Okay. The applications are focused on the European case studies. Basically, my experience with practitioners is in Europe, even if I had a talk with some US railway company, and I have also projects with Chinese railway, but using different methodology. So I will focus most on the European problems using this alternative graph methodology. First one I want to mention is the real-time traffic management. For the real-time traffic management, the literature is divided in different types of problems. They go from train control problem, where you control the speed of trains, to dispatching problem, where you control a small network that is under the control of one dispatcher, or you can go to larger problems at a network level, and then you deal with problems also of higher complexity. So going back to the local dispatching is the starting point where we can apply this type of methodology. And indeed, if you look at the literature and if you look at the practical application of this methodology, the single line can be a reference. In practice, the alternative graph methodology was applied on the metro line in Italy, in Milan, was applied to a single line network in the central of Italy and in Norway. All these applications were with, I would like to mention Professor Mannino about this. But the problem is that going from a single line real-world application to a dispatching area real-world application, there is still a gap in the literature. I will talk more about this gap later on. Now, was just to introduce the local train dispatching. Here, we are enlarging the network from a single line to a number of lines and a number of minor stations, or just a large complex station area. Here, I spent my PhD on studying this type of problem, and there is a good literature on the train dispatching. Then another application okay, before going to another application, I mentioned a special type of train dispatching application that was for the on-time European project, where the train dispatching was combined with the speed control. Here, they developed an alternative method where you coordinate the speed of trains in one layer, and in another layer, you optimize railway traffic flows. The second layer, the higher level, is made with an alternative graph-based methodology called the AGLIBRARY, and the overall software is called Roma software. So here you are iteratively optimizing the sequencing, routing of trains, and speed control. Then if you move to a more network-wide problem, you move to a so-called global train dispatching problem. What is the difference between local train dispatching and global train dispatching? The difference is the size of the network and the number of dispatchers, human operators, that are involved in the decision process. When you have a global dispatching, you have several dispatchers. Imagine that each dispatcher has a local dispatching tool, a local alternative graph that is helping locally to take decisions. Then you have another layer that is a coordinator layer, where again, you can use an alternative graph, but with a higher level representation of your network. And this type of approaches, there is a literature that was developing first, so-called border graph, that is a graph just to check feasibility, and then a coordinator graph based on the alternative graph methodology that is for finding a globally optimal solution at a network level. And then, of course, you need to iteratively exchange information between the two layers, the local dispatcher and the global dispatching, to find a globally feasible or even a globally optimal solution. Then an additional type of complexity is when you start looking at different types of disturbances. Of course, if you have a single delay train, your tool might easily recover a feasible solution, might easily recover the timetable if there is a delay, or might easily find a feasible schedule for the trains. If you start having a more complex disturbance, you might have a more advanced tool. And also, if you think about the human decision maker, the more you have delays, the more it becomes difficult for the human decision maker to take the right decision. So when you have multiple delayed trains, it's more and more important to have a global conflict detection resolution, finding where are the problems and finding a good solution for those. And this is even more complicated when you have disruptions. Disruptions means some trains are running at a different speed than planned, so a lower speed. For example, there is heavy rain on a track, then the trains must go at a lower speed than the timetable. Or you have even problems in the track. So some signaling system is not working, the switch is not working, you need to close some track, you need to use alternative routes, but there is less capacity in your network. And then you need to find a way to find a feasible solution. Then another thing that we need to mention is that the type of formulation might depend on the type of network. Of course, if you have a metro line, is very different that you have a conventional rail network is different that if you have a high-speed network. And then you also have to consider passenger demand. There is an increasing stream of research that is dedicated to incorporating passengers into the decision-making process. And along this stream, there are applications, again, of the alternative graph methodology to both optimize train traffic flows and also passenger flows. So passenger enter into the loop, into the decision-making process, and you can make use of this methodology to decide, for example, on the passenger route choice. Okay, then I move to another problem that has some issue in common. The issue in common is that we again need to find a train schedule, but the train schedule has to be found at a tactical level. So a tactical level is not during operations, is 1 day or 1 week or sometime anyway before operations. And usually, at least in Europe, the tactical train timetabling is based on an existing train timetable. So you have a so-called set of service intentions, and you want to find a solution that that satisfy all your service intentions. Service intentions are a set of business rules and objectives related to your train traffic flow. One special problem that we are dealing with in collaboration with the Swiss Railways is how to insert new services in your draft tactical train timetable. You can imagine that inserting a new, for example, freight train into the network might generate a very interesting gain for the railway company, especially if you do this at low cost for the other services that you have in your timetable. So this problem in terms of alternative graph is dealing with a very hard problem in finding a feasible solution. You need to use a lot of release and deadline constraints, so strong constraints that are related to the existing business rules, and you need to find a way to insert your new train service in the schedule. Another type of tactical timetabling problem is dealing with how to design timetables for dealing with emergency situations. For example, this problem was studied by me and other people at the UDEFT in collaboration with the Dutch Railways. They wanted to develop timetables that can be applied to recover special emergency situations. So when there is an emergency, means that there is a strong disturbance, disruption. You cannot imagine to apply the existing timetable, the draft timetable in ideal conditions. You need to apply a new timetable with low capacity in the track, with a low number of services, but you need to decide the right services. So you can see here an example, just to give you an idea. There is a problem on one track, then you can either continue running a lot of trains in the left sides, but with a lot of waiting time. You see a lot, some train is waiting, this is space, this is time, is waiting for a long time. Or you can reduce the number of services by canceling services, globally rerouting trains on other tracks. And then you can see that, of course, the waiting disappears, but also the offer to the passengers is less. So we need to find a good trade-off to offer to the passengers, if it's a passenger timetable, for dealing with emergency situation. The emergency situation has also problems related to the transition between the original timetable and the emergency timetable that can be nicely dealt with alternative graph methodology. Then, okay, I want to continue. Another type of application of tactical train timetabling is to assess special characteristic of the timetable. For example, you can coupling the traffic scheduler with a traffic simulator, and you can assess nice properties of your timetable, for example, related to the robustness to disturbances. How much do I need to absorb a disturbance? How much nervous is the system? How often do I need to change the schedule? So you can assess the timetable before the operations. Then you can also think about investigating which is the best set of routes to give to the traffic controller. And you can do this at tactical level. So filtering the possible combination of routes, it's an interesting problem. Train routing selection problem is the name that is studied and can be applied in this field. And then you have a very big number of integrated train scheduling problems that are dealing with, for example, integrating the train schedule with maintenance scheduling, both train or track maintenance, or you can have integration with the rolling stock scheduling and staff personnel scheduling. Then a third type of application is related to the capacity consumption. This application, I had experience with TU Delft. We did a work for the Dutch government that have to invest on a new type of signaling system, and we had to study the capacity consumption while changing the signaling system. This type of application is a kind of way to apply this tool to simulate traffic flow. The traffic flow simulation can be done in normal traffic situation or even in disrupted traffic situation. Regarding the project for the Dutch government, we deal with the so-called dynamic infrastructure occupation problem, where you need to try to understand which is the capacity consumption. We're dealing with a number of changing factors. For example, stochasticity of delays, response to the signaling system, the type of signaling system, even the signaling system positioning, the signal positioning, so the signaling configurations, and then even the forecast on the traffic control action, how to deal with conflicts. You have as a result an idea which is the capacity of your infrastructure with different settings. Then you can use this type of tool to evaluate different type of railway infrastructures. For example, we were studying a problem with we have new lines and how to run traffic flow on these new lines. Or you can deal with, again, different types of resources, the different types of availability of resources. Okay, now I have 10 minutes to deal with the one specific application. So now we'll focus on one application. Okay, initially I wanted to describe for this application that is train scheduling. Mathematical models, algorithms, and a test case. I will reduce my presentation to mathematical models and test case. Okay, I will just mention quickly the algorithms. Now, why do we need to deal with train rescheduling? Let me say some more few words motivating this application of the methodology to this problem. The first problem is that we need a model that is able to highly precisely present the traffic flows. Then we need to have a model that is able to solve any type of disturbance, for small disturbances to serious disturbances. Then we need to find a high quality solution, so global conflict resolution. And all of this in train rescheduling must be done quickly. To have an answer, to have a tool that is able to deal with all these issues, we have to consider a number of modeling techniques, combine them. First of all, I need to mention the level of the level of granularity that we need. We need the level of granularity of blocking times. This is a level of granularity where, as you can see from the feature, you deal with the position of trains, you deal with the distance, minimum required distance between trains, taking into account the signaling system, the train protection system, the time for the driver to look at the signal, and many other aspects. So the level of detail is very high. Very important to have this detail in your train rescheduling model. Then how can we use this type of detail to combine with the alternative graph to detect potential conflict and solve them? I want to show you this with this example. You have again a blue train, two trains, and a red train. They are going to share a number of resources. So you have the blocking times of both trains represented. They just touch in a station. They do not overlap, so the solution is feasible. Now we want to represent as an alternative graph. Here you have the entrance of each resource, each train and each resource that is an operation. And then you have arcs representing running from one operation to another one. So from one piece of track to to one position interact to another position, and the position are delimited by signals. And this is for the blue. Then the similar idea you will have for the red, and when you fix the weights of these arcs, you take into account the running time. Now you will need also to model the sequencing. If you have that the blue one is first and the red, then it's easy. You just insert these arcs that are green arcs because are sequencing, representing sequencing decisions. And then you need to give a weight. The weight of the alternative arcs is based on the minimum required head distance between trains. Then you have a number of business rules, for example, related to the time in which the blue and the red train are expected to enter in your network. And then you can, through these constraints, compute the longest path to reach each node. That is the earliest start time of each operation. And then you can, more in general, represent the problem as an alternative graph, in which you had as an additional complexity where, as you can see here, you have a pair of arcs for each pair of trains, because here you want to decide which train goes first, the blue or the red. This is the alternative graph representation that was introduced by Machis and Pacciarelli. And you might have other business rules, other constraints, for example, the planned departure time from one station, or you might collect delays in station that are in the middle of the line or at the end of the line. And then you might select a feasible solution, that means selecting for each pair of arcs one arc and giving a timing, a start time to reach operation. This is the first level decision, sequencing. The second level decision is the giving a start time of each operation. When you have decided sequencing, giving a start time to each operation can be reconducted to a shortest path problem in graph theory. Okay. Or alternatively to finding the longest path from a starting node to a ending node in the graph. Okay, how do I represent the alternative graph as a MILP, as a mathematical formulation, mixed integer and linear programming formulation? We will introduce continuous variables for the starting time of the operations and the binary variables for the sequencing of the operations. So you need to give a weight to each arc, you need to give a name to each operation, and a start time to each operation. For example, operation 1 has start time T1, and this is the weight of this arc going from 1 to 2, W1, 2. Once you have this definition, this information for all your trains, then, sorry, for all your operations and arcs, then you can introduce the mathematical formulation. Okay, let's see quickly the mathematical formulation, how it look like. As I told you, each constraint is an arc. So if you look at the black arcs, you will end up with a constraint for each black arc. For example, let's look at this arc. This means that you have T1 variable, timing variable T1, must be equal or larger than T0, assuming that T0 is 0, plus the weight of this arc. Okay, so you end up with this constraint. In a similar way, you can model these 4 types of black arcs. If you want to model the blue arcs, for example, let's model this one, then you will write T2 must be equal or larger than T1 plus the weight of this arc. And similar for the set of red arcs. For the green arcs, these are pair of alternative arcs. Then you need to pair them. How do I pair them? First, you introduce each of them in your formulation. So for example, T7, this arc is formulated like T7 must be equal or larger than T2 plus the weight of this arc here. Or this other arc here, okay? So T1 must be equal or larger than T8 plus this weight. Now, how do I put together those 2 arcs? Because I need to select only one of those 2. Then I need to introduce a binary variable, let's call it X, and then introduce a big M, okay? I don't go into the detail, but it's easy to model this. At the end, you, for example, want to select always the red one goes first, and then you might end up with a number of binary variable set to 1, and then you might have your solution, your sequencing solution. Once you have a sequencing solution, you can compute through the longest path problem the timing of each variable. For which timing variable, the start time of each timing variable. Okay, now here I highlight that the fact that if I want to select this arc, then this x must be equal to 1, and then you have this constraint in your problem, while the other constraint will disappear through the big M. Now, I have 2 minutes to talk about algorithms and application. The algorithms that are developed in a tool that I want to mention, AGLIBRARY, are based on the decomposition for type of variables. First, we optimize the train scheduling, where inside this box you have timing and sequencing variables, and then you optimize the routing problem. So you change the routing of some trains. There is a literature about this, and there are a number of algorithms, either heuristics or an exact method for the train scheduling problem, and there is a stream of research on the train routing problem, mostly based on heuristics. So ways to develop a local search and ways to improve the local search to, for example, taboo search, variable neighbor search, or variable neighbor taboo search. Then application. I mentioned one application that is in collaboration with Alstom. They have a traffic management system. They need to add intelligence, and we use AGLIBRARY to add this intelligence. So the system is giving information, input information to the optimizer, the scheduler, and the scheduler is giving back the optimal schedule. Application I want to mention is the UK network nearby London. Here is the London city. And this is the type of level of detail in our application. Is, as you can see, very low level of application. Why do we need such a level of detail? Because it's a real-time train scheduling problem, and we need to incorporate signals. Why do they need our support? Because they realize that in a complex station, they might have problems to understanding how to find a feasible solution during operations. So to recover feasibility, sometimes they need to cancel a lot of services. Through intelligence, you can avoid to cancel too many services and quickly better converge to a feasible solution. Here, for example, you have a situation in which you have a disruption. So this is what you have, and during the disruption, this is what you have new. You have as new that either you go very slow in one direction, or you wait that the disruption over, and then you run your trains. In this type of situation is a disruption situation. Now we try to see what are the results for this collaboration. These results are from 2013. After those results, we got better results in terms of optimality and computation time. And I also need to mention that other researchers who are working on this, for example, from the University of Bologna and the University of Padua, and they also find good results. But the important here is not the results, is to show you the application, what type of application. Application was on this type of network, and which is the best way to recover disturbances. We compare a general solver through a MILP formulation, Cplex solver from IBM, with the AGLIBRARY solver based on the alternative graph methodology, and we found that the general solver may have problems in finding a feasible solution for some instances, may fail, while a customized solver might always find the feasible solution. Regarding optimality, the general solver might be better if you give a long computation time, actually slightly better, just one more optimum, but the average computation time is not applicable to real operation. It's more than 1000 seconds for the general solver, while the customized solver might take a few seconds on average to find the solution. So it's more applicable during real-time operations. Just one last slide, because time is over. This is a demo that we did at Alstom. This demo was to show to the railway manager and to the railway dispatcher how to apply the optimization-based rescheduling tool in a closed loop with a traffic management system. Okay, thank you very much for the attention and interest in my presentation.
Yeah, thanks a lot, Andrea. That was a very inspirational and a very thorough presentation. We got quite some questions over here, so we can go directly to them. First of all, it is regarded to the objective function. So consider you have the same feasibility space and trying different objective functions. Did you see changes in computation times? And
yeah,
in general, you reason about it, Abad?
Yes, in general, yes. We need to discuss it with the two different possibilities. If you use a customized solver, when you change the objective function, you might lose some nice mathematical properties that we're using to speed up the resolution process. So your performance might decrease in quality significantly. And this means that you need to think about the algorithms a little bit. You need to better customize the algorithms to solve the specific problem. If you go for a general solver, you might have less control on this because you might be lucky and have good performance with some objectives, less lucky with some other objectives. Again, also you can imagine that in the general purpose solver, there are some algorithms solving the problem, and in some cases, the algorithms can better use of the objective function formulation, other cases less. But it's in general probably less sensitive on the objective function, but it's more difficult to predict the performance beforehand with a general purpose solver.
Okay, clear. So then the second question is about using AGLIBRARY for modeling moving blocks. Do you have some experience already? And could you say something about the performance of such model?
It's a nice question. Actually, many years ago, around 2000, there was a project I mentioned in my presentation, Combine2, where they were reading using the alternative graph methodology for the moving block signaling system. So many years ago, more than 20 years ago. After that, the scientific community was focusing on first solving the problem with the current signaling system and infrastructure to have quickly an application in practice. But there is a stream of research, not much, on the moving block technique. I have to say that you need to significantly change the set of business rules and objectives and to significantly customize your alternative graph approach to the moving block. So I did not do this personally, but I think it's nice research. And from what I have seen in the literature, there are already some very nice results in, for example, Computational Research Part B journal, some publications about
that. Okay, sounds good. Then the next question from Muhammad is about computation time for finding infeasible and a feasible solution. So could you comment on that one?
That's very interesting. I would like to answer for the infeasibility first. There are basically two types of infeasibility. One infeasibility that is detected by the fact that the given set of business rules are infeasible. And this type of infeasibility can be quickly detected by the alternative graph methodology, because you will, even during the preliminary solving process, you may find a positive length cycle in your graph. So very quickly find an infeasibility. The second type of infeasibility is much more difficult because it's due to the sequencing decisions or the routing decisions. So when the infeasibility is connected to your decisions, this means that the only way to prove infeasibility of the solution is that you may explore the entire solution space. So this problem is an NPR problem. It can be very difficult to solve. The other one, feasibility. Okay, feasibility means optimizing a certain objective function. Optimizing a certain objective functions might be quicker when you have good mathematical properties. For example, if you solve the objective functions of type makespan, that means minimizing the maximum of something, for example, maximum delay, maximum completion time, or similar. There is a literature on the scheduling theory that helps you a lot in computing an optimal solution quickly. If you start changing the objective function and moving to more strange objective functions like average weighted delay or similar, then it might be more difficult to find an optimal solution and prove optimality.
Okay, thanks a lot. One question from Hamed. It's about maintenance operations. And so far in literature, we see maintenance windows mostly scheduled as virtual trains. Do you have any experience or some alternative ways how alternative graphs would be considering maintenance operations over a long periods of time?
A long period of time? Okay, I try to answer first the formulation. The formulation of the maintenance of the track is simple. It's just a job with the release and deadlines and some special processing times that basically does not allow any train to use the resource for a certain time, or the group of resource for a certain time. The other type of maintenance is about, I don't know if you want to talk about also the rolling stock maintenance, but it's less easy to discuss in this with this methodology. Long term, I don't understand very well. If you enlarge the prediction and then you want to study the maintenance, you can do it, but the size of your graph will increase. You need to find a good trade-off between granularity of time and resources and optimization of your prediction horizon.
Okay, and we can have one last question now. It's about the accuracy of travel times. So how would you assure accurate travel times for real-time rescheduling of traffic in complex line and station networks?
Very nice question. You need to go for a decomposition approach, or two ways. One way is a decomposition approach in which you have a preliminary optimization of train trajectories, and those optimized trajectories goes as input to your alternative graph model. Or you could also think about having an exact method in which you optimize the speed control, and in which basically you need to set up, you have different possibility to insert arcs in your graph. And this possibility need to be explored. I tried this second approach, but the problem sites might explode quickly. So if you go for an integrated optimization, you might solve small instances. If you go to a two-step approach, it's very practical. For example, there is a combined project and the on-time projects, European projects, well-known European projects, especially the second one, that show that it's feasible to optimize speed trajectory and then optimize sequencing and routing in a two-phase approach.
Okay, thanks a lot. Well, given the time, I would like to then close this session. I'm very thankful to Andrea for a wonderful presentation, and thank you all for joining this webinar and for very active participation in Q&A. So we are formally done, but I invite you to stay around. Andrea will be more than happy to stay longer. So if you have any other questions or follow-up, we would like to catch up with him, feel free to stay on this call. Thank you very much. And I hope to see you in about a month from now for our next webinar. Thank you so much and have a great day.
Thank you.